All right, guys. This should be an interesting problem. So we're going to do number 59. Long John Silver, a pirate, has buried his treasure on an island with 5 trees located at the point. So here are the 5 points. All measure relative to the origin in this figure. His ship log you instructions to start from tree A. Okay, so basically you have 5 points and there's a treasure buried somewhere within, and here are the instructions. Now what I'm going to do, folks, is I'm going to write I did solve this before, so I'm going to get my answer sheet here. I don't know where it is. Oh, it's right here. I'm not really going to look at it, but what I'm going to do is I'm going to read you the instructions and I'm going to write the vectors as they come about. But first, let me write these points here. So here are the points. So the instructions are, let's see what it is. His ship logs, okay, to start at tree A. So we're going to start at tree A, wherever that is. So I'm going to put R1 as in the first position that you're going to start is at that vector A. So this is how I'm going to write it, folks. So once you start at vector A, then you move towards the direction towards tree B, but cover only 1/2 of the distance between A and B. So that's another way of saying that R2, whatever that is we're going to start at A, but we're going to move into the direction. So that means that we're going to take the difference between vector B minus vector A, and we're going to cover 1/2 of that. So that's going to get us to the point R2, whatever that value is. And R3 is going to be, so notice, folks, that I'm just writing all this information down. Then you move towards the tree C, covering 1/3 of the distance between your current location and C. So that means that you're going to start at R3, and then you're going to move towards the direction of wherever C is. So that's going to be C minus R3, and we're going to cover 1/3 of it. And that's just so, and then we're going to start from to get to position 4, we're going to start at position 3, wherever you lie in that point, and we're going to cover 1/4 the distance between where you are and D. So we're going to do the same thing. We're going to move in the direction of D. So whatever the difference between these vectors are is going to be the direction, and we're going to take 1/4 of that. And then we're going to do R5. Last but not least, R5. Finally, we're going to move towards vector E, covering 1/5 of the distance between E, and then you start to dig. So now the treasure is going to be wherever R4 starts. So wherever this starts, we're going to take the E vector, and we're going to take this direction, and we're going to cover. All right, folks, so we're going to take R6, and we're going to be defining that to be where the treasure is at, which is likely going to be in R5. So it's somewhere in this map. So what I like to do, folks, is you could either plug these values in and get the result right away, or work this out, which I already did this. I'm just going to copy the answer that I have in the end. I'm not going to do it on this video, but I could. Is think of this where the treasure is at. This has some variable R4. We can replace R4 with R3. We can replace R3 with R2. So this is going to be R2. And then we can replace R2 with R1. And then back with A. So basically this R4, this whole equation R6, is going to have mainly just these variables, A, B, C, and D. And once you work everything out, conveniently specifically for this problem only, then the end result would be vector A, vector B, plus vector C, plus vector D, plus vector E, all divided by 5. That's going to be the end result for this problem. So once you work everything out, and I like to do it all in one go because, you know, that's just the way I am. So let's answer the question. So assume that you have correctly determined the order in which the pirate labeled the trees, A, B, and C, and D, and E, as shown in this figure. What are the coordinates of the point where the treasure is located at? Well, that's going to be my variable. So where's my cheat sheet that I have here somewhere? Oh, it's right here. So the answer is going to be 10 and 16, I believe. So once you add this up, you have 20, 80, 70, 110. 110 minus 70, that's 30, 40. That's going to be 40. Wait, what? This is going to be 30. Okay. So that's going to be 50 then. Okay, with an extra 10. Okay, so that's going to be 50. And 50 divided by 5 is going to be 10. And this would be 60, 60, 50, or 50, 20, 80. 80 divided by 5 would be 16. So the answer for part A is going to be R6 is going to be in the vector 10 and 16 meters. That's where that's the end result when you add them all up. For part B, well, this is part B right here. That is going to be that equation. So because B is asking what you do if you do not really know the way the pirates label the trees, what would happen to the answer if you were entering in the order? Or that's another way of saying whatever order it is. And state reasoning to show that the answer does not depend on the order which the trees are labeled. Well, once you label it the way I do, or however you guys want, and solve it in terms of in terms of all these vectors combined, then this would be the final result. And if you look at this, the order here does not matter which order you start with which. So likely, whatever the end result is, whatever R1 that you start with, because remember folks, this is in terms of whatever these final components are, and they could be anything. But ultimately, they're going to have these variables in the end. So it really doesn't matter of the order. So the order is, I think the word commutative, I think that's the, whatever that terminology, if you're taking stats, is. So no, the order where they label that does not matter. All right, guys.